Hi, my name's Doug and welcome to Catch a Big Vision here on Emerald Hill Skies. The goal for tonight's live stream is to explain to maybe what it would be like to a 5-year-old. And I have a specific 5-year-old in mind. I have a friend named Ross. He has a son named Judah. Ross and Megan tell me that Judah is very interested in science. So Judah, for some of this program, we'd like to direct this directly to you. So Judah, welcome. I want you to know that we're designing this so we can speak just directly to you, and I hope explain some of the things you can see in the night sky. For the rest of us, though, we're here together on Emerald Hill Skies. I just want to welcome you as well, whether you're watching this live or later on the YouTube recording. Welcome to Emerald Hill Skies. We observe from the outskirts of Louisville, Kentucky. And let's get right started because we've got Jupiter on the screen tonight. Now, let's get started and talk directly to you, Judah, and other 5-year-olds and young people maybe your age or close. You know, we live on this planet, and I've got just a little prop here. We live on this planet Earth, and you know, we can pretty much find our spot where we live. It's here in what we might call the United States of America. So I'm trying to look at this backwards. We're here in the middle of the USA. Now, I don't know where you are, but wherever you are, it's kind of a similar place on the globe. I want to make sure you understand that the globe is the thing that's turning. The world is the thing that's turning. And as it turns, it's always turning like this. Now, there's a light that's right there shining on the globe. I don't know if you can see it, a little reflection of a light. See if I can point at it right here. Let's pretend like that is a star shining down on the Earth. So the way this works is these stars are out in space, and as the Earth turns around, the same star stays in the same place up in the sky. It's the Earth that's turning. But as the Earth turns, it looks like to us that the stars are swinging across the sky. So if you can imagine a flashlight out here being one of the stars, as the Earth turns on its, we call it the axis, or it's, you know, if you consider like this globe, it has like a stick down the middle. As the Earth turns on its axis, those stars are visible to different people, and it's the same set of stars are visible to all those folks. But there are some things that do wander around up in the sky, and they don't stay in the same place. We have one of those visible tonight on our screen, and it's the planet Jupiter. Now, Jupiter is a giant planet, and it has several moons. And I thought tonight we ought to try to pick out some of these moons. So I've got a map of the sky. And the great thing about this map is it stays automatically in, so it can match what's happening to Jupiter's moons. So right here we have the moon Callisto. That's the map view. But over here in the live view, there's Callisto right there. And this is the moon Io. And right here we have in the live view, so this is what our telescope is seeing. We have an 11-inch telescope out there, about 200 feet from where I'm sitting. And this 11-inch wide telescope is helping to magnify things, helping to look at things a lot closer. So there's Io. And then we've got the planet Jupiter. Now on this side, we've got the moon Ganymede. And there's the moon Ganymede. Oops, sorry. Need to switch back to our screen. There's the live view of Ganymede up in the sky. And then the map shows us that we've got the moon Europa down here. Let me just zoom in on those a little bit closer. And as we do this, our image might dance around a little bit more. It's atmospheric disturbance. Just the air is bouncing around, but you can see a little bit closer now the moon Europa. So just like the Earth has a moon, a giant moon up in the sky. Jupiter has moons, except we just have one moon. Jupiter has lots of moons. Now, I was kind of hoping we could see another moon tonight that's really close to this moon right here. I don't know if we're going to be able to see it. Just a little bit too much atmospheric disturbance. Probably not going to be able to see it tonight. There's another moon that's right here that's a lot dimmer. And since it's dancing around so much, I don't know if we're going to be able to see it, but we're going to try to do something called live stacking. And it's going to change things around quite a lot. So we are going to be able to see it. Let's get things sorted out here a little better. With the help of live stacking, I think we might be able to see it. So all these different colored, it almost looks like you're at a parade and you're seeing confetti. All that different colored confetti is what we call atmospheric noise. And that atmospheric noise, it's just the, like all the light pollution, for instance. Around Louisville, people leave street lights on, and they leave, you know, maybe building lights on, great big spotlights on. Sometimes people shine a big spotlight up at a building, and all that extra light makes Louisville look really, really bright. So let me see if I can show you a picture of the sky. Now, in this picture of the sky, maybe you can see you see my pointer there? Look down here close to the horizon. Look at all that light. Well, that's from the city of Louisville. This is a live view. It's through a different camera that's mounted on top of the telescope. And there's a picture. On the right, you can see that camera. It's for the adults, it's a ZWO ASI 178 monochrome camera, but it's a lot more sensitive to light. And there you see it. On the left side, you see it mounted on the top of the telescope so that it can get these big, nice big pictures of the sky. And this is all the light pollution. So here's what I would say. Help your mom and dad and the business people that you know. Maybe if your dad has a business, help them remember to turn off any lights that you don't need. And these would be like big lights that are shining on billboards or all the lights that are shining up in the sky. Help them turn all those off, and that'll help us reduce some of the city light pollution. Now, another thing that's polluting the night sky tonight is the moon. And this is the moon up here in the sky. It's shining about 3/4 of the brightness that it would be if it were a full moon. So it's getting close to the point that it's almost a full moon. In spite of that, we can see, let's get back to our live picture, we can see this image that's stacked. I don't know if we're going to be able to make it out. We're rejecting a lot of frames here. Let's try a different way to do this. Let's try doing this at maybe 100 and reduce this to maybe make this 8 seconds. And then let's reset this. Let's try this again, see if we can get a little bit better picture. And meanwhile, look at the folks that are on. Larry, welcome from another part of Kentucky. Tiffany, good to have you here on the live stream as well. That's too much, isn't it? Let's take it down to 2 seconds and clear and start again. Would really love to get a picture of the moon that's right there beside, right here beside Ganymede, and it's the moon Amalthea. Amalthea. And I've never seen Amalthea before, but I thought it's just barely far enough away from Jupiter that if we took our picture exactly right, I was hoping that we could see Amalthea. And this is a little better. Still, Jupiter's glaring a little bit too much. Take this down to, we're still rejecting frames. No, we're not going to be able to see Amalthea tonight just because of the atmospheric disturbance. So I'm sorry about that. We'll try Amalthea another night. So I'm going to go back out to full, stop live stacking. Go back out to full and take one last look at Jupiter. Again, this is a live shot of Jupiter and its 4 moons. Tiffany, good to have you aboard. Dennis, good to have you. Ricky from Florida. Ray, good to have you on from Arizona. You guys are all the usual suspects here. Storms in California. Sorry to hear that. Okay. Well, so this is the way astronomy is. Sometimes things work, and sometimes they don't. We're gonna delete Amelia and Amalthea. Pretty sure I had added Amalthea down here somewhere too. There's Amalthea. We're gonna delete them, and then we're just going to make a quick entry on the rest of these because we were able to see, first of all, out here, if you're keeping track, we were able to see Callisto, which is out here. So I'm going to say, create a log entry for Callisto. Make sure that all this is correct. And it is. February the 18th, this all looks good. We say, Callisto looked bright and beautiful. And we were able to see Io right here, another moon of Jupiter. So if you were living on Jupiter, what do you think this would look like? Try to imagine what this would look like. Oops, I keep clicking the wrong thing. I need to say L. I need to say L. Io was shining.
Telescope position synchronized. Telescope position synchronized.
And let's see. Then we were able to see Ganymede right here. Ganymede shows up really well, huh? And we're able to see right here, we're able to see Europa. Europa showed up well. Okay, Ganymede, Callisto, Io, Europa. Awesome. All right, Now I'm just wanting to jump over. Now that's a planet, and it moves around in our night sky in different places. But the next thing we're going to go see is a star. And this particular star, we're going to move the telescope over to this star
The
now.
telescope is slewing.
And you'll see the sky kind of start spinning around there. And here's a picture of the telescope spinning
View
around. It's a live view of the telescope. Now, if it looks bright out there, almost bright as day, that's because the moon is shining so brightly. And this is a camera that's designed to work in the night sky. Now this next thing we're going to try to see is a planet, and you know, it really, I mean a star, it's a star in a triple star
Viewing
system.
Hyades.
And what we mean by triple star is, you know, when we look up in the sky during the day, how many suns do we see? It's not a trick question. We just see one sun, don't we? But when we look up, when we look up in the sky in this system, we see more than one sun. Just going to do a check here. Here is Cade, and there is STF 518b, and here is STF 518a. So this star in the middle is the star that you would look up and see if you were on the planet Vulcan. If you've ever watched the show Star Trek, then you know that they refer to the system that Vulcan is in. Now, I just want to be honest with you. The Star Trek is not a real show. It's not like Truth. But sometimes it mentions things that are real. And one of the things it mentions is this, this star here. This is the sun that Mr. Spock would see if he were to look up in the sky where he lives. But the thing is, he sees more than one sun because there are 3 suns where he grew up. And sometime when you're watching Star Trek and they go to like a movie or the show Starship, you know, the Enterprise, Star Trek, when you're watching that and they go to Vulcan, and if they show the sky, notice that they'll show at least 2 suns. And that's because this is a binary system. That's what you call it when there are 2 suns and your planet is spinning around 2 suns. It's a binary star system. Now the strange thing is there are lots of stars that are binary star systems. Some people say as many as half of the stars that we see in the night sky are actually binary star systems. So the planet Vulcan is one of those, and this is the very sun that is the bigger of those 2 suns that Mr. Spock would look up and see at night. So that's kind of fun. Stu, good to have you aboard from down in New Zealand. Dave, good to have you aboard from the Eastern Plains. And P. Lark, thank you very much to remind people to hit the like button. Dennis Luttrell is saying, what, Star Trek isn't real? So I just thought we ought to stop by and see this star because it is, at least, you know, in the show Star Trek, it's a part of the fun kind of plot there, isn't it? Okay, so that's the star Keid, K-E-I-D, in the constellation Eridanus. All right, so that was kind of fun. Now let's go to a a planetary nebula. And we're going to go to the one that's called typically the clown face.
The telescope is slewing.
So again, there's the sky spinning around. Here you can see the telescope moving. And that's a live view of the telescope out in the observatory. Let me just check the temperature out there.
Viewing clown face.
It's 30.7 degrees. And every time we change by 2 degrees, I notice that things get a little out of focus. So sure enough, we're going to be out of focus in a while, but we're okay for right now. Look how the telescope's aiming almost directly straight up. That's because
clown face.
This particular object is high, high, high up in the sky. And if you were to go out and try to look up at it, you would have to look almost straight up. Let me see if I can find a way to show you how it would look if you were to look straight up. So here's where you would have to look. See those little, oops, let me turn back to the screen. Here's another map of the sky, except this map is a map that shows the whole sky. And so you kind of have to imagine that you're standing out and you're able to look up and see the whole sky. See that blinking little X? Tiny, let's see if I can make it bigger. Is that getting bigger? There you go. See that blinking X? Well, that blinking X is where you'd have to look. And right here is straight up. So it's almost straight up in the sky. And let's get a different view so you can kind of see some of the sky around this place, because I think while it's doing that, let's start this thing to let us see this a little bit better. Let's do this. And this is NGC 2392. It's sometimes called the Eskimo Nebula too. All right, now let's get another map up so you can see. Let's show a little bit closer view. Let's look at this one, this map. Okay, so let's suppose you were to look toward the south. So maybe have your mom or dad go out with you and look south. And then viewing south, now raise your head almost directly up in the sky. And you would see two bright stars here. This is Castor and Pollux. And these two stars are here in this constellation, and right there between those two bright stars and down a little bit is the clown face. Now, right here in the middle of our screen is the clown face, and we're going to zoom in on it now. The clown face is a planetary nebula, and let me see if I can explain what a planetary nebula is. When a star is like a big fiery ball. It's just a big furnace. It's like a big ball of gas that's on fire. And when that ball of gas starts running out of some of the gases that are really the most fiery, when it starts to run out, the star kind of begins to burn out a little bit and shrink. But when it shrinks down, it begins to get tighter and tighter and tighter and compress. And when it squeezes together, now it sort of fires back up again. Like if you've ever done a campfire and you see the campfire starting to burn out, and your dad maybe takes a stick and maybe puts all the sticks together a little tighter, and the fire catches back on fire, and maybe some coals come out, and you see these little sparks flying up in the sky. Well, that's what's happening to the clown face, otherwise known as the Eskimo Nebula. it started to burn out. And when it did that, it sent out some sparks and a whole bunch of gases out in the sky. And when it did that, it made a shell around it that looked like this. Now some people think, let me zoom in, I'm really pushing our telescope a little past its ability, but some people think this starts to look like a clown. I think it looks a little more like an Eskimo with a furry hat on. This is the furry hat. But for the adults that are with us, adults, see if you can see the central star. How about that? Now that is the central star that it ejected all this gas. And this probably happened years and years ago, and that gas is traveling out at a fairly fast speed, but we are so far away from it that it just almost looks like it's standing still to us. And back in the old days, before people had telescopes that were very powerful, they had some telescopes, and they would look at this and they would think, well, that looks like Jupiter. You know how we were just looking at Jupiter, and it looked a little bit bigger than a star point? Well, they thought this must be another planet, except they could tell it had a fuzzy appearance around it. And the word we use when something's cloudy like that is the word nebula, because that's what nebula means in another language. It means cloud. So they said, this is a cloudy planet. And actually, I can see where they would have thought that, can't you? It looks like there's something inside of here, and then it has clouds around it. So I can understand why they called it a planetary nebula, a cloudy planet. Now we know it has very little to do with a planet. It's not revolving around our sun at all. It's very, very far away. In fact, this planetary nebula is so far away that it's 3,400 years for the light to arrive from that star to us. We call that a light year. Every year, the amount of space that light travels in a year, we call a light year. And that planetary nebula is actually 3,400 light years away. So that's a long ways, maybe not very far by the standards of the universe, but it's pretty far in our standards, isn't it? We're going to take a picture of this tonight because that's a pretty cool image of the clown face or Eskimo nebula. For you adults, this is NGC 2392. It is a beauty indeed, Tiffany. By the way, Judah, if you're watching this after the fact, there are some people that are watching live, and I'm trusting you're already in bed. But there are some people that are watching live, and I get to talk to them. As they message me over the internet, I can see the messages that they're sending. And Tiffany lives out in California, and she's often here with us watching things live with her little doggie, which is a Shih Tzu, by the way. And Tiffany says, what a beauty. It really is. Let's make it a little bit bigger before we go, even though it's going to be a little fuzzy to us. Now, for you adults, we're now pushing a full 400% past our optical zoom. So you can start to see a little bit of that pixelation happening, adults. See that the image is kind of broken up by the pixels, but on the other hand, it does let us see the structure of this planetary nebula, doesn't it? Now, Judah, maybe you can see this is that dying star. And look at this inner layer that looked like the inside of the clown face. What's happened is this dying star has now ejected 2 different times. So maybe your dad, Ross, got in there and stirred up the fire twice. And 2 different amounts of sparks flew out. And these are not really sparks. They're like gases, and they're being lit up from the back. And maybe sometime when you're out on a trip with your dad and mom, Judah, maybe you'll see a neon light, maybe in the subway store, and it'll say open. And your mom and dad will point it out. And you'll notice that it looks sort of like a tube of gas that's being lit up. Well, that's what this is. It's like a bunch of gas that's being lit up by the star behind it. They call it, I know adults, you're aware of this being ionized, when an electron is being cast off and another one is being caused to light up and re-electronize, you could say it in other words. It's lighting up that gas. And it makes a pretty picture for us, doesn't it? Okay, well, unfortunately, we've got to go now. On to the next target. And next, just looking here, we already saw Keyed. Let me just make a note of the fact that we stopped to see the clown face. Just going to hit the L button, and I'm going to say, wow. The Eskimo Nebula. By the way, for you adults, in case you're wondering, I did mention to the developer of the software, SkyTools, that the focus of my typing was changing to the list, and it was causing shortcut keys to bring up other screens. And the developer said, no, that's impossible. And I sent him a video of it happening, and he wrote back and said, you know what? It is happening. I'm so sorry. He said that'll be fixed in the next update. So he is fixing this. The Eskimo Nebula looked amazingly Eskimo-ish tonight. This just helps us, Judah, helps us keep track of what we've looked at. Now I'm looking at my little list here, and what this list is, it reminds me of what we're going to go look at, and I can see things that are maybe starting to fade away a little faster, and I can choose what we should look at next based on as the Earth rotates, some of these objects are going to be disappearing, you see, because the Earth is rotating, and they're going to be going down behind the woods. Here where we are, they're going to be disappearing behind the woods. And that's sad, you know. So let me figure out which object we ought to go to next based on what might be disappearing. I'm thinking we might ought to go to the Triangulum galaxy. So let's head over there next. And the Triangulum galaxy is sometimes abbreviated M33. So Judah, here we go to the Triangulum galaxy, or M33. I'm going to say, I'm going to tell the telescope to
The
go.
telescope is slewing.
The Triangulum galaxy, M33. Now what it slid past there in that picture that's over there on the lower right, it slid past the moon. And that was particularly bright in the night sky, wasn't it? Now look how the telescope's lowering.
Viewing Triangulum galaxy.
Lower and lower in the sky, huh? So we wait until the telescope settles a little bit. After it has moved to a new spot, it's still jiggling a little bit. It's like vibrating.
Viewing Triangulum galaxy.
Larry says, I've been wondering what M33 would look like in EAA. Okay. So then what we do, our software changes into a different mode, and in this mode, Judah, I'm going to describe to you now. Put your thinking cap on, because this is a pretty This is a pretty important thing to learn. This picture you see here is the way the night sky would look if we just looked through a telescope with an eyepiece. And as you can see, it's kind of hard to see anything. So what we do is we use a camera for the eyepiece. And when we use a camera for the eyepiece, it lets us see the night sky a little better than we would see it with our eyes. Now, why is that? Well, because for one thing, when our eyes look at something, we always see it exactly as it's happening right now. And in fact, I think if I remember right, our eyes take something like 25 different pictures per second. Every single second that ticks by, our eyes are taking 25 different pictures. So they're taking a lot of pictures very fast. When God made the human eye, He made it in an amazing way so that we could see things that are amazing. But it doesn't help us sometimes at night because since our eyes are taking so many pictures so quickly, we can't take in as much light. So what we do with the telescope is we slow down the process. We open up the shutter, so to speak, and we let more light in. Not only that, we take that picture and we save it. And then we take another picture and we save it. And then we take another picture and we save it. We take another picture and save it. And we keep doing this over and over again. And then we average all those pictures together. Now you could think of it with the word add, if that's easier for you to think of, but it's actually averaging. And when it averages all those pictures together, look at what it can see. What we're zooming in on here right before it descends behind the woods. Now this part over here to the left is a tree. But look right here in the middle. It's a galaxy. And look how it has a spiral shape just as it starts to scoot behind the tree. Notice what else? We got all this light pollution from Louisville. Remember, turn off your lights at night, please, because all those lights that are on at night are ruining the night sky for us. But right here in the middle, look how we can see something amazing. And this something amazing is another galaxy. And if you look very closely, you can see some spiral arms. Now, did you ever see a whirligig? I wish I had a whirligig here to show you. I wish I had a whirligig because then you could see all the different spirals there. Maybe your mom or dad will show you a whirligig sometime. But look at this spiral that's kind of starting to show up here. And this spiral here. I also think it looks like what's in the bottom of the blender or the ice crusher or the, help me out, Megan or Ross, what is this? A food processor, that's what I'm trying to think of. It reminds me of the bottom of a food processor. Maybe Megan, you can show Judah what that little thing looks like in the bottom of the food processor. Don't touch it because it has sharp blades. But that's in a way what this galaxy looks like. It has these whirligig spirals that kind of extend out from the edges. Now notice all these pictures that we're adding together, they're helping us to see this galaxy in a lot better way. Now right now this galaxy is looking pretty big in our screen, but it's actually really tiny. I don't know how to tell you what 61 arc minutes is. It would be about 1 degree. So imagine if you could take a picture of the night sky and divide it with 180 marks. Just one of those little marks would be the size of this galaxy. But what we've done here is we've zoomed in on it with this telescope. And what this telescope allows us to do, see how it's pointing up at that galaxy right now, it allows us to be able to see in that sky, we can see this image. Now, how in the world do we see an image in that sky as bright as it is? Well, it's because we're adding all of these little 20-second time exposures. We open up the shutter and we let the camera look at this galaxy for 20 seconds solid. And then we close the shutter, we take another picture, 20 seconds, and we keep adding these all together. John on our live stream is saying it kind of reminds him of a whirlpool. You're kind of right. Thomas says, Jesus died for all the sins in every universe that has humans or humanoids. You're right, Thomas. If all those stars there in this Triangulum galaxy, if they have other planets and there are people who live on those planets, Jesus had to die for them as well. So, Larry, you were wondering, what does M33 look like in EAA? This is it. Now, I want to just remind you, if it were a very dark night, when we didn't have this bright moon, see the bright moon up there in the sky, Judah, that moon is kind of ruining the view for us. But look how it's not ruining the view totally. And that's what I kind of like to prove to myself, that in the middle of a city like Louisville, with all this light pollution, and with all of the moonlight that's shining, and the galaxy's about ready to disappear behind a tree, and the lower an object gets in the night sky, the more air you have to look through to see it. And you guys know, adults, we call this air masses. And as we look at this galaxy, we're actually looking now through 3 different air masses because it's so low in the night sky. It's so low close to the horizon. So we're looking through 3 atmospheres now at this point. And it's 3 million light years away. So the light that's been coming from this object has been traveling 3 million years to get to us. And tonight, our little 11-inch telescope grabbed all those little particles, photons, that were traveling in all those waves, and it splatted on the mirror of our telescope and caused our sensor, when the mirror flashed it up to our little camera, not that one, this one, when the mirror flashed it up to our ASI 2600 MZ Pro camera, it caused us to be able to take this picture of M33. It's kind of fun, isn't it? Okay, so we're gonna make a log entry, and we're gonna say, in spite of, I'm gonna wait for a second because our cursor jumps down there. In spite of the 3 air masses, the light pollution, and the moonlight, the 74% moonlight, we could still see the spiral arm structure of M33. And I want to tell you, Judah, a lot of astronomers, a lot of amateur astronomers, people with telescopes, they don't even come out when the moon is this bright. In fact, this program that I'm using down here, this program helps us decide what images to go look at. When I called up that program, it said, don't even bother going out tonight because it's so flooded with moonlight. There's going to be so much moonlight, you can't even see anything. That's because this program thought that I was going to be using an eyepiece. And I would be staring into a little eyepiece live. So I'd look up at the sky, and I'd look down at an eyepiece, look at an eyepiece, and you know what? They would be right. There'd be no way we could see the Triangulum galaxy if we had to rely on looking into an eyepiece. So what we do is we rely on this camera to capture our frames and combine them together. And this whole thing together is called electronically-assisted astronomy. EAA, that's the abbreviation for it, EAA. The other thing I like about using EAA is Tiffany and Larry and John and Dennis and Dave and Stu, all the way down in New Zealand. Stu is on, and Stu lives in Tauranga, New Zealand. Maybe someday Ross or Megan can help you look up Tauranga, New Zealand. And the cool thing is, Stu is able to observe side by side with me, just like we're in the same room because of this way that we observe. So I love this kind of astronomy. It's like we're a team observing together. All right, well, that's all we're going to be able to see tonight of M33. We just got to move on. And it's just 6 minutes from disappearing behind the horizon. Let's go catch the Andromeda galaxy because it's 11 minutes from disappearing behind the horizon.
The telescope is slewing.
Now the Andromeda galaxy is
Viewing
2.6.
Andromeda galaxy.
It's 2.6 million light years away. But the thing about the Andromeda galaxy is that it's so big. And you know, really, as far as our targets go, it's abbreviated, by the way, M31. As far as our targets go, look, we can almost see it without live stacking. Look right there. We can see that little core of the Andromeda galaxy right there.
Andromeda galaxy.
And what our magic software here, SharpCap, is doing is it's moving it to the middle of the frame for us automatically. So it's figuring out where the Andromeda galaxy was on the telescope's view, and it's centering it for us. Pretty nice software, isn't it? And now it's going to start taking those pictures and stacking them. Now, Andromeda galaxy is just 8 minutes from disappearing behind the trees. And it's looking through 4 air masses right now. In other words, Judah, it's looking through a lot of air. But in spite of that, look how we can already see part of the Andromeda galaxy here. I'm going to tune up our view a little bit. And what these adjustments do down here, Judah, these adjustments help us compensate for the light pollution. And we sort of make up for the fact that the city of Louisville is so polluted with light. Now, this is a unique view of the Andromeda galaxy because we get to see not only the Andromeda galaxy, we also get to see extra galaxies beside it. And to be able to help us see those, I'm going to pull up our map again of the night sky. And let's see how, when we look at the Andromeda galaxy, we see not only M31 here, but we also see M32. I'm sorry, we see M31 and we also see M32. And then we also see, here this big thing is M31, this is M32, and we also see M110. So we see 3 galaxies side by side. And then, by the way, all these other things that we see are what's called globular clusters. And a globular cluster, it's a bunch of stars traveling together. So let's zoom in a little bit on Andromeda. Now this galaxy is huge. It is 130,000 light years across. And I don't know how to put that into perspective, 130,000 light years. It is so big that it has different arms out here. If you look very, very closely, you can see how there's a little bit of dust that is separating the look of this arm from this arm. what we can also do is we can use our fancy software here. It's called SharpCap, and it will show us officially what are the different objects that we're seeing here. And look how it says, here is M31, and it says, here is M32. Now watch what it's saying. It's saying if you back off to the big picture, you can also see the third galaxy here, and that's M110. So we're seeing 3 galaxies at once. So let's go over here and zoom in on M110. Let me get rid of our deep sky image annotation here. Let's go look at M110. So what is a galaxy? A galaxy would be like millions of stars, maybe billions of stars, maybe a trillion stars, the biggest number you can think of stars, traveling together. And they're like a kind of a island of stars. There's so many of them and so many of the gases that go with them that it's a whole nother galaxy. Now, do you know what our galaxy is called, Judah? Try to remember what our galaxy is called. It's the Milky Way galaxy. And we didn't know what the Milky Way galaxy looked like. Because why? Because we live in it. Until the first astronomer saw this galaxy, and somebody figured out, wow, that's probably what ours looks like. So we live in a galaxy like this. And the way we first figured out what our Milky Way galaxy looks like is by studying this one. And as it turns out, our Milky Way galaxy is a friend to this galaxy. They sort of travel through the universe together. 2 friend galaxies. And M32 travels with M31. And M110 travels with M31. And our galaxy, the Milky Way galaxy, travels with M31. And all together we call this a galaxy group. And it all travels together. It's a lot of stars. Oh yeah, Tiffany is looking at my shirt here, and it says something like, I need my space, and has a picture of a telescope on it. My friends here at work, they got this for me because they knew that I did this observing at night. Well, we're going to have to say goodbye to the Andromeda galaxy, but before we do, I'm just going to do a quick little log entry here. I'm going to say we could see, I'm going to stop typing while it moves the cursor. We could see the dust trails separating the spiral arms, even though Andromeda was just 8 minutes from disappearing behind the trees. And now, guess what? It's just 1 minute from disappearing behind the trees. Now you might be wondering, Judah, maybe you're asking, how do I know when it's going to disappear? Because I've told this software what our tree line looks like. Very, very careful measurements. So the software knows, oh my goodness, that galaxy is about to go behind the trees. So we're going to go look at something else real quick before we disappear behind the trees, because you can imagine it also sinks our telescope very low, and finally our telescope starts to complain. It says, wait a second, I wasn't designed to go this low. Let's go up to this object, which is a kind of cluster. And let me stop this live stacking. Remember, it's been taking those pictures and it adds them all together, so I really should turn that live stacking off before we move. So let's go to the Hyades, which is also known as OCL 456.
The telescope is slewing.
Now, this object is in the constellation Taurus, and it's 14 light years away, so it's a lot closer. I'm sorry, it's 150 light years away. 150 light years away.
Hyades.
So it's a lot closer, and it is just really what it is a cluster. We're going to put the name here, OCL 456. The Hyades. And we're going to go look at,
Viewing Hyades.
we're going to go look at an atlas. It's just a bunch of stars traveling together. And it's called an open cluster. And while we're here, let's look also at what it would look like if we looked outside, like if your mom or dad took you out. What you would want to do is look toward the west. So ask your mom or dad to help you figure out which direction is west. Basically, it's going to be in the direction of the sun sets. So here in Louisville, you would want to look toward, Evansville. And then you'd want to look up about, right now tonight, if you were going to go out and look, you'd want to look up about maybe 36 degrees. Now, there's a way you can find 36 degrees. If you put your fist down here even with the ground, that's 10 degrees. And then stack this fist up on top of it, that's 20. And this will be 30. And then about halfway up, so 3.5 fists would tell you about how high in the sky to look. And that's where you'll find here in this constellation called Taurus. And you might wonder, well now, what does the word constellation means? It's not really identifying something that travels together in the sky, but the stars look like they're together to us. And so long ago, people that would be on camel rides or out at sea, traveling on a ship, way long time ago, back in the days of the Greeks, in the Bible times, people would see these shapes and they would try to imagine what do those shapes look like. And when they saw this one, let me see if I can zoom in a little bit, they saw these things that are extending out and they look like horns. So they said, well, that looks like a bull, because they thought these stars made a shape of horns. So they called it Taurus, and Taurus means a bull. Now, if you zoom in on Taurus, and now we're going to go back to our star map that's way zoomed in, you see this cluster. It's an open cluster, Hyades. Now we can listen to a description of Hyades if we just double-click this object in the list.
Hyades is an open cluster in Taurus. It is magnitude 0.8, with an apparent size of 5.5 degrees. This open cluster is 150 light-years away. It is 14 light-years in diameter. Its stars formed out of a cloud of gas and dust 787 million years ago. Hyades is also known as OCL 456, and Calendar 50. Note brief from, My Attachments. C041, Mel 25.
Okay, that's getting into the notes that I've made, and it's just a bunch of numbers and stuff. But here in the star map, you can see kind of a picture of what we're looking at. And here you see this cluster of stars. And this cluster, all of these stars are traveling together. It kind of looks like a swarm of bees, doesn't it? It just looks like a swarm of bees. And what we do is we measure the distances to these stars with some complicated way, Sort of like, did you ever go by a policeman? And the policeman maybe was measuring how fast your car was going. And he held a thing out that looks sort of like a radar gun, you know. Well, we use something kind of similar to that to figure out how far all these stars are. It's not exactly the same, but it's kind of similar. And that shows us that all these stars are about the same distance away, and they're traveling in the same direction also. So not only are the same distance, but they're traveling in the same direction. Dean, good to have you aboard from Michigan. And Tiffany, thanks for helping people feel welcome. By the way, if you've tuned in late, tonight's a little bit different night. We're trying to help people get the big picture, a big vision for astronomy. And we're aiming this partly for adults, but also we're zooming in on kids as well. And we're really zooming in on one young person. His name is Judah. He's the son of a friend here that we have at the office. His friend's name is Ross, his wife Megan. And Judah, this broadcast in part is for you. You'll listen to this, I hope, later as a recording. And look at this swarm of bees called the Hyades. Okay, so we're just going to check this off. It's about 18 minutes before it would zoom down a little bit too low to look at. So now we're going to put a log entry about the Hyades, and we're just going to say it indeed. I'm going to pause because the cursor is going to go away, but the developer is going to fix this. It indeed looked like a swarm of bees. Now, there are a lot of open clusters in the sky. We're not going to look at a lot of them, but I think we should go look at one more, and let's go look at it next. It's called the Pleiades. So let's stop this livestock. I really like the Pleiades because I'm going to put here the name M45, and we're going to slew to the Pleiades. Slew means move.
The telescope is slewing. Viewing Pleiades.
I really like the Pleiades because not only is the Pleiades an open cluster, but also the Pleiades happens to be traveling through a bunch of dust in the night sky.
Viewing Pleiades.
Good to have you aboard, Corin. Where are you viewing from, Corin? Where are you observing with us from? Because the Pleiades is traveling through a lot of dust, I really like it because it is lighting up that dust in such a way that the dust becomes part of the special view that we see when we look at the Pleiades. So we see a combination of two things. Remember us talking about the fact that the word nebula meant cloud. Well, this open cluster makes its own cloud light up because as it's traveling through the night sky, it has encountered a whole bunch of dust. And as a result, when we look at the Pleiades, look at the way this dust is lighting up. Now, some people say when they look at the Pleiades that they can see a little tiny dipper. Let's see if you can pick it out. They see this star here. See if you can pick this out, Judah. They see this star here, and then this star here. And then they see that star, and that star, and then this star, and then this is the spout. The spout. Now, if you look very closely, you can see a star here. So look, you can see this handle, and you might even be able to see that star. So you can see this handle, and then you can see this little bowl, and then this little spout here. And your mom might use a dipper like this to pour the gravy onto the turkey at Thanksgiving time. So Megan, see if you can find a gravy, what do you call that? A gravy, Tiffany, what is that called? A gravy has a special name. They don't call it a gravy dipper. A gravy, what is that called, Tiffany? A gravy, I can't think of it. Ladle? Maybe, that might be it, a ladle. So Megan, you might have a gravy, whatever you call that. I think there's another name. Is it boat? Throat. Seems like it rhymes with boat. I can't remember the name. My mom used to use the word, and I can't remember all the way back then. Now, some people think that this particular open cluster, which is called Pleiades, or M45, some people think this is the Little Dipper, but that's not true. But it does make the shape of a Little Dipper. Now let's see if we can call up a gravy boat, Junk John says. So it is a boat. That's what my mom would always say anyway. Thank you, Junk John. Let's call up the big overhead sky map. And see this blinking light over here? That's where Pleiades is right now. It's just 46 minutes from sinking too low to observe. But if we were to go look at the Little Dipper, it would be in a completely different part of the sky. Let's close this map and let's open up this map. So we're viewing the west. So looking toward, almost the same as when we were looking toward Taurus. Remember the bullhorns? This was Taurus. And by the way, this little red line, this represents the tree line at the place where we're observing. And that's how low the Pleiades is. Now if you look at the tiny grouping of stars, that's how tiny the Pleiades is. By contrast, the Little Dipper, I wonder if I can turn this. I'm going to try. No, doesn't let me turn it. But I tell you what, I think we can turn this one. Now this is going to be zoomed in on Pleiades right here. But let me zoom out for a second. Too many stars, right? There are Taurus, the bullhorns. I'm going to try to grab it. Sure enough, it's letting me turn this. Now it's drawing all those new stars. As I turn it toward the north, this would be the direction of the real Little Dipper. I think what I'm going to do is call up another program. This is a good use for the program called Stellarium. Now, Ross and Megan, you guys could install Stellarium on your laptop. And the cool thing about Stellarium is it's free. And in its first installation, it doesn't take up very much space. So just Google the word Stellarium, Ross and Megan, and get a laptop that you can use, and Google the word Stellarium download, and you'll be able to go there. Whatever kind of program, whatever kind of laptop you have. It doesn't matter whether it's Windows or what. And then when you open up Stellarium, use your magnifying glass here to search for Polaris, and you'll see the North Star. And what we've done with our copy of Stellarium, Judah, now, think about it, these are the trees at Emerald Hills. And we've actually taken a picture of the night sky, and we've taken a picture of the trees during the daylight a little bit, and we've kind of colored it so that you can actually see the trees at Emerald Hills and look at the shape of the stars. So now we're looking due north, and this is the real Little Dipper. So you can see it's a pretty big constellation. But now we're going to spin Stellarium toward the west. Now this is toward the west. And remember, here are the horns of Taurus, and right here are the Pleiades. So now we're going to zoom in. Now zoom in with me, Judah. Notice how we're starting to zoom in. Look how small Pleiades are. What I'd like to dare you to do, next time you're on a trip with your dad or mom to a dark place, look out toward the west and try to find the Pleiades, and look, see if you can find these stars in this shape. And see if you can find this little tiny dipper just with your naked eye. What would really be cool is if you had some binoculars, because this shape shows up amazingly well with binoculars. It's M as in Michael, M45, stands for the guy who first cataloged it, first wrote it down, Messier, Charles Messier. And if you see a Subaru, Ross, someday when you're looking at cars in the parking lot of Kroger, show Judah the logo for the Subaru car on the back of the Subaru. And guess what Subaru uses for their logo? Pleiades. Because why? Because Pleiades is, in Japanese, Subaru is the word for Pleiades. This is the word they use for the Pleiades. And so Subaru is the name of the Pleiades, and that's why they have the Pleiades on the back of the whatever Subaru that you find. By the way, I want to show you one more thing while we're in Stellarium here. If you keep on spinning Stellarium around, Judah, you'll recognize this. This looks down toward the barn at Emerald Hills. So Pleiades is right over the top of the look at the barn. And then if you keep spinning around and you keep turning, this is where I park my truck at night when I'm doing observing, here in the observatory. And you'll see the observatory, and here is, Judah, our main building at Emerald Hills. And I sit right there in my office and operate the telescope from here inside in my shirt sleeves. And the telescope is out here in the observatory, and it's cold out there. It's 27 degrees out there right now. So it's very cold. So there's a little orientation in the night sky. Dean is pointing out that the North Pole is a double star. You're right. And Junk John is right. Pleiades is also called the Seven Sisters. Now, we've waited long enough so that now we can look at the nebula that is around M45. And this is what I've been doing, stalling a little bit so that we could see the clouds that are around these stars. So what we're going to do now is we're going to zoom in, and all these stars have a name. This one might be called, well, let's call up our Alice again and let's find out. Oh boy, we got to zoom out now. I mean zoom in. I went the wrong direction. Sorry. It's going to be faster. Here we go. Every one of these stars has a name. Let's see. Alcyone. Merope. Merope. Maya. So I think this one's called let's see if that's Merope. What's that star? Okay, Merope. Yeah, I think this is Merope. And look at all, not only is there cloud being lit up, but also you can see dust in like little trails. Now, a lot of people think this is a hydrogen or whatever, an oxygen nebula. It's not. It's just dust. And this Merope star is bright enough that it even lights up that dust. Some people used to that the dust was traveling with Pleiades, and maybe this is all that's left, but now we know that that's not the case. The dust has a different speed and it's traveling in a different direction. It just so happens that right now in our time, Pleiades is traveling through this dust, but they're unrelated. But it makes for a beautiful picture, doesn't it? Look at this dust here. Isn't that beautiful? So Judah, this is what dust looks like when it's lit up by stars. Now, where could you see this? If you go sometime to a big church like Southeast Christian Church, and maybe your dad can point out when they start spraying fog over the stage, and then they shine lights in it. You see the fog lighting up with the light? Well, that's what we're seeing here, except it's not fog, it's dust. Charles Messier was looking for comets. He did not know all the smudges he was cataloging were galaxies. Right, Chris. Yeah, I want to take my telescope out tonight, but not at 24 degrees. Too cold. You're right. It is too cold. How could we sit out there in 27-degree weather for very long? All right, so Judah, can you remember what this is called? Remember? It's called Pleiades, or M45, or the Seven Sisters. All right, so we're just going to do a quick log entry here. We're going to say we could really see the clouds, the cloudy dust around Merope tonight. Okay, now this is an open cluster, but let's go next to an asteroid. Let's close out this live stack. We probably should take a picture of that. That's pretty beautiful, isn't it? Really, really beautiful. I think God did a good job making this for us. Dean says, can you point out the seven sister stars? Yeah. Let's back off a little bit more. Because they're a little easier to see once you back off. 1, 2, 3, 4, 5, 6, and most people have a hard time seeing the seventh when you're using a naked eye. But they show up really well to us here because of the telescope. So this star is harder to see. Let's look at our atlas and see what is the magnitude of that star. Let's see. Boy, there are so many bright stars here in this cluster, it almost gets lost, doesn't it? think 1, 2, 3, 4. Oh no, wait. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So that's SED 19C.
SED 19C is a likely H2 region in the constellation Taurus. Its magnitude is unknown.
So this star.
Seleno is a suspected variable star and a multiple star in Taurus. It is a B7 subgiant. Seleno is 330 light-years away. The variability of the star is dubious.
5.45 magnitude, so it's barely visible to the naked eye. Whereas these main stars, that's Atlas, it's 3.6. That's Alcyone, it's 2.9. That's Merope, it's...
Barnard's Merope Nebula is a likely H2 region in the constellation Taurus. Its magnitude is unknown, with an apparent size of 30 arcseconds. Barnard's Merope
Merope. 4, magnitude 4. Electra, magnitude 3.7. Seleno, that's the one that's hard to see, is 5.4. This one is... I did have this one memorized. I think it starts with an M, doesn't it? Maya, yeah. Maya. And it's bound to be magnitude 3 as well. Zoom in a little bit till we can see Maya. Yeah, 3.9. So it's not very often you have that many stars so close together that are magnitude 3. They're just blazing. 1, 2, 3, 4, 5, 6. And then this is the 7th that's harder to see. It's almost like a vision test. But it's not a fair vision test because these stars are so bright that they sort of keep you from seeing this 7th one. Good question, Dean. Junk John says, I'm a big fan of the Pleiades. Junk John wrote out all the names for us. Cool. All right, we're going to take one more picture because we stayed a little while longer. All right, now let's head toward that asteroid. Tell you what, let's go to a different asteroid first. Let's go to Metis. We've been to Vesta before here on the channel, but we've never been to Metis before. Let's go there first. Metis.
The telescope is slewing. Viewing, 9, Metis.
Metis, huh? You know, I'm afraid the moon is going to be too close to this object. Let's look at our sky view for a second. Yep, look, we're looking right smack into the moon. So I don't know if we're going to be able to see this or not. I can't imagine that we'll be able to see this. Staring right at it. Is Stellarium still open, or did we close it? we closed it. Let's go back up to Stellarium because I think Stellarium will show us our difficulty. Corin just imaged Metis. Or maybe you're talking about M45, Corin. All right, so let's try to look for M45. No, sorry, Metis. It's not the right Metis. Let's call it parentheses 9 Metis. Oh, see, that's where Stellarium is going to let us down. It isn't informed about Metis. So let's just look at the moon. It's informed about the moon. Okay, so there's the moon, and there's where our telescope is pointing. So this might work. Let's see what the number of degrees is between the edge of the moon and our telescope. Oh, it's just 4 degrees. Yeah, I'm afraid that's too close. I don't think we're going to be able to look at Metis tonight, folks. It's just too close to that dastardly moon. Just 4 degrees. That's bright, isn't it? My goodness. So we're going to remove Metis from this list. And we're going to go to, let's go to Eleonora. It's another asteroid I'd hope to look at tonight. Or Juno. Let's go to Juno.
The telescope is slewing.
Sure, that's bright. Well, you can see why people don't come out when the moon is that bright. It's just a little bit of a hassle, isn't it? Let's get away from the moon and try to find Juno. It's in the constellation Leo tonight. And Juno is one of those wanderer objects. You know how I said in a lot of the sky, the stars stay in the same spot in the night sky, and as the Earth turns, we can always find them in the same spot. Well, this is not one of those stars. This is an object sort of
Viewing
like
3, Juno.
a planet. But it comes from a
Viewing
belt.
3, Juno.
It comes from a belt of objects that are planet-like, but are really not big enough to be called planets. I mean, Juno is a mere 290 kilometers wide. What do we have, guys? Stu, what does it take? A kilometer? Is it something like more or less 1.6, I think, or 1.65 kilometers per mile, so not even 2 per mile. So 300 kilometers might be maybe what? About 200 miles. Can somebody Google that for us? 300 kilometers, would that be 180 miles? 290 kilometers. I think it's about 180 miles-ish, wouldn't it be? So 180 miles, that would be like the distance from here to Indianapolis. So what this is a rock the size of the distance from here to Indianapolis. Now to try to find this rock, I'm just going to zoom in, and right there it is. Right in the middle of the screen. How do I know that that is Juno? First, because if we put crosshairs in the middle of our screen, it's very close. And our telescope is very accurate at finding these objects. The other thing is, look how these stars mostly are kind of like points. But look how this looks different. It's almost out of shape. Let's go into 200. See how it kind of looks ovalish almost. Now the other interesting thing is, if we were to start tracking this object, we're at 200% right now of our camera. If we were to start tracking this object, over time, and it would take it some time, but over time, in comparison with all the stars, this object would move. Yeah, Dean says 180 miles. Thanks, Dean. Oh, is the scope cam the main screen? I'm sorry. Thank you for telling me, Chris. This is Juno. And notice how it's kind of warped looking. If we go into like 150%, it's kind of warped looking. Look how these stars are kind of round. By the way, they're just a little bit out of focus now because of the temperature change. 27.1, and we started at 32 degrees. But as the temperature changes, it gets our telescope out of focus. But here is Juno. I'm going to just do a quick little log entry. Juno doesn't look that much different from all the other stars, but it does look just a tad oblong, oval. It's 100, did I say? 200. 290 kilometers, that's 180 miles wide, and around, let's see, 110,000 kilometers away. That would be about, let me do the quick rough math here, that would be about 4.5 light minutes. So it takes light about 4.5 minutes to travel here from this little asteroid Juno. Tell you what, let's do. Let's go out to Google and let's say Juno Wiki. I should say Juno Asteroid Wiki 3 Juno. And here is what Juno looks like if you use a giant telescope. Look how it's kind of a little bit misshapen. It's a little bit oblong. And because I'm used to looking at our telescope, I can tell Juno doesn't quite look like a star pinpoint. It looks like this, except tiny. Well, that is a big, 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 big enlarged picture of Juno. You're looking at it right here. So now you can say, I saw an asteroid. All right, now let's look. Now that's another asteroid. Let's skip past that for right now. Oh, let's go see it. It won't take us that long. Let's go see an asteroid that's so tiny. It's called Herculina.
The telescope is slewing.
Herculina.
Viewing, 532, Herculina.
This is magnitude 9.8.
Viewing, 532, Herculina.
Okay, I see Herculina. Herculina is right here in the middle. Look how it looks very tiny. If we use our crosshairs again, right here in the middle. Now let's zoom in. It even looks like a little rock. Herculina. And it's 532 Herculina. So let's search for 532 Herculina. A three-dimensional model of Herculina. Wow. So this is what Herculina would look like. Three different views of it. Herculina is a rock that's just 367 kilometers around. It's a little bit farther from us. It's about 12 light minutes. Now while we're here, let's look up main belt asteroids and show a picture of this. Okay, I know it's very bright, it's probably hurting our eyes, but look at how you have, so Judah, back to you. See how you have the sun, and then the next planet out is called Mercury, the next planet out is called Venus, and then our planet, Earth, then Mars. Then on the other side of Mars, you see this big belt here. And this belt is filled with rocks. And some of those rocks are big enough that they're almost big enough for us to see. And this is one of them, 532 Herculina. Now the 532 means it was the 532nd asteroid that was discovered. Lots and lots of asteroids, and then next comes the planet Jupiter. So it's a whole belt, a whole circle of asteroids traveling together. Kind of fun, huh? Okay, let's get rid of that. And let's get rid of that. And let's go back and take one more look at Herculina. So these are rocks that are rotating, they're revolving around our sun, kind of like the Earth is, except they're just tiny. We could see something different about Herculina from the start. Just looked like a tiny rock. Now, what we would need to do to prove that this is an asteroid is take pictures and then 5 nights later take another picture. And if we did that, we would see that this asteroid would have changed locations. It will move among the stars. and maybe very slowly, but it would move. That's because it's revolving around the sun instead of stuck up there with all the stars. Okay, now let's go see the remains of, oh wait, let's go see a comet. Let's go see C 2017 K2 Pan-STARRS.
The telescope is slewing.
It is 236,000 kilometers away. So that would be about, what? Maybe 60 light minutes. Yeah, we're going to say 60 light minutes. So traveling at the speed of light, which is what? What is it? 187,000 miles per second. It's very fast.
Viewing C/2017 K2 Pan-STARRS. Viewing C/2017 K2 Pan-STARRS.
It still takes maybe an hour for light to travel to us from this comet. That's far. This is C 2017 K2 Pan-STARRS. You might wonder why the funny name. Well, the C says it's a comet. 2017 says it was discovered in 2017. The K tells us what month in 2017 it was discovered in. It's kind of an odd way to tell months, I admit it. The first 2 weeks of January would be the A part of the year, and then B is the second 2 weeks. C is the February, D. E is March, F. G is April, H. I is May, K would be June. So this was discovered the first 2 weeks of 2017, and it was the second comet discovered during those 2 weeks. And it was discovered by the observatory team that calls themselves, they use the name Pan-STARRS, or the observatory telescope Pan-STARRS. And this is a special telescope that searches for comets all the time. It just takes one picture after another all night long and uses computers to try to figure out which ones are comets. Okay, so what we're doing here, again, we're live stacking. And we'll just zoom in right away to 100%. Right here's our comet, right there in the middle. And you say, well, how do you know? It's just because now, those of us on the channel that have been looking for these, we've learned little by little to pick out the comets. You might say, Judah, don't comets have tails? And they usually do, eventually. But it just depends on where they are in relation to the sun, how far away they are from the sun, and also, is there something blotting out the light of the tail? And maybe on a moonless night, there would be a tail. But at least we can see a little bit of fuzz around this star. And notice how it's a little bit greenish, and that's what comets tend to be, a little bit greenish also. Now there are several comets that are going to be visible in the coming months. So keep your eyes out for comets because they come and go. Oh my goodness, I can't believe we forgot Uranus. Let's call it a day here and go directly to Uranus.
The telescope is slewing.
So what are comets?
Viewing Uranus.
They are balls of rock and ice.
Viewing Uranus.
Soot, charcoal, chunks of lead, all kinds of stuff that have bunched together. Sometimes they get so bunched together that they kind of bond. They kind of bond together. And then they travel, some of them decades, in and out, close to the sun and back out again. And some comets have a very regular flight around our solar system, and others don't. So you have to observe them to figure out the orbit, the circle that it makes around the sun, and then try to calculate how close it'll come to Earth, and that helps you figure out what the tail is going to be like. So here's Uranus. And you notice it has some moons with it. So let's call up our atlas. Where is Uranus again? Oh, there it is. Okay, so wow, you can see Miranda and Ariel out here at the edge. Okay, so here's Uranus. Miranda's out here at the edge. I'm going to zoom in a little bit, even though it's going to mean that things are going to pixelate a little bit. Here's Miranda. And here's Ariel. Here's Umbriel. And here's Titanium. Oh, I got it backwards. There's Oberon, and there's Umbriel. Oberon. Well, now let's figure this out here. Let's take another look. That is a star, so that's that star. I wonder if we can, I figured out the other night how to rotate this. Anyway, that's Titanium. I figured out the other night how to rotate this. How did we do this, gang? Maybe we use the eyepiece view. Now this is where we're going to be able to rotate it. See those three stars here are those three stars there. So watch. We can rotate this around and put those three stars exactly where they are in our camera image. Try this again here. And once we get this rotated, it's a lot easier to tell where things are. Copy? Copy that? You with me? Okay, so there's Uranus. Now let's zoom in. These are all stars. Even though they're in a straight line, those are stars. Star, star, star. They all have names, by the way. God gave them names. These are not God's names, but they're humans' names. Oh, that's a star. And that's a star. And that's a star. How about that? Star, star. Well, this is not very helpful, is it? What in the world? Why aren't those on there? Oh, it's because it's eyepiece view. Now I wonder if we go back to Atlas, if it'll show us. Let's go back to Atlas, if it will have rotated it. Did it? Didn't, did it? So that star is here. That star is out here to the right. So what we're trying to do here is be able to identify the moons. Judah, thanks for hanging with us. See how these stars are in the same shape as these stars? So that helps us know the orientation. So we start here and we say, here's titanium. Now let's zoom in on Uranus. So there's a moon here, and that's titanium. And then there was a moon here, that's Miranda, Ariel, and Oberon. Now let's drop out a live stack. And I think live stacking is not really helping us that much. Well, it was helping us more than I realized, wasn't it? Let's put this back on 3 seconds and dial this up to like 400. Oh, it's because it's going down in the trees. There goes an airplane, by the way. Anyway, we saw it. It's just that now, sure enough, it's going down in the trees. Sorry about that. My bad for not noticing it quickly enough. All right, let's get on our way to the next object, which is going to be the Crab Nebula. We're not live stacking anymore.
The telescope is slewing.
Okay, so we're going to say we saw Uranus.
Viewing Crab Nebula.
bothersome in that. Barely caught Uranus with Miranda, Ariel, Titania, Oberon, and Umbriel. It's kind of like naming like elves or something, isn't it? What I'm doing here is just quickly logging this. Okay. Larry wondered if we're going to try to do a Messier marathon this year. I don't know. I have mixed feelings this year just because we have done it now 3 years in a row, and I kind of, in a way, have gotten beyond it, you know? But maybe I should, just because it's a tradition. The first 2 years, the first year we were the only group to do it in the world, amazingly, but that was partly because people weren't out observing much because of COVID. Okay, so we're here on, get rid of these and this. Okay. Oh my goodness, our focus. We're going to have to focus here. There's just no doubt about it. We should be able to do the Crab Nebula with this focus, I think. But then we've got to focus. Let's quickly put the Crab Nebula in the middle. So when a star that's real big starts to burn out,
Crab Nebula.
It behaves differently than the stars that were smaller and burning out. If a star is real big and it starts to burn out, it explodes at the end of its life. We call that a supernova. Well, we're looking at the remains of what happened when a star burned out around about 1067, was it? Yeah, you're right, Larry. It's a long, hard night, but the other thing is you only get about 3 or 4 minutes on each object, and normally we're doing 7 minutes per object. And that's because some of these objects take 7 or 8 minutes to see. So sadly, the other thing about a Messier marathon is you just get a lot of poor images of things. On the other hand, you do see a lot in one night, right? But you see a lot of poor images in one night. I've noticed it just really takes sometimes 7 or 8 minutes. And I know that with the observatory where it's built, by the way, Judah, there's a picture of the observatory with the telescope in the middle. But the observatory where it's built and this building in the way, we can never see M30. So we're never going to improve above 109 objects. And we've already done, as a team, all 110, because one of the other observers that's not here was able to spot M30. And then also the first year we did it, I actually moved my telescope to be able to see M30. So we've done 110 2 years in a row. Last year I did it by myself, but with the telescope mounted where it is in the observatory, we will never see M30. So last year I did 109. That's all we'll be able to do again. So I'm thinking, do I want to go ahead and try to do it even though we're not going to be able to see all 110? So I haven't decided fully. What do you guys think? Should we do it? Good night, Ken. Good to have you aboard. You guys help us decide. Do you want to do it? I mean, I don't think all of you all want to stay up all night long, do you? Typically, we have to go to work the next day. Okay, so Judah, this is the remains of that supernova star that blew up and got really bright. And then after time eroded away a lot of that brightness and all the remains of all that, like maybe you might think of it as, did you ever come across maybe something like a dead bird and it had been laying there for a while? Well, that's kind of what this is. It's like a dead bird that's been laying there for a while. This is the carcass. Carcass means a dead thing. This is the carcass of a supernova. It blew up and was incredibly bright. It was so bright that it looked like a star in the middle of the day. You could see it in the middle of the day for what? 2 or 3 weeks. And then at night, it was blazing for weeks afterward. And then it just started fading. And we know this because there were Chinese astronomers who kept these records. It was like 1,060, something like that. Well, this is the remains of that supernova. It's called M1, or the Crab Nebula. You can see it has some color to it. Judah, can you make out any greens? Starting to see any greens? What about reds? This is the limit of what we can zoom in with our optical zoom, but we can zoom in with our digital zoom a little bit farther. And look how it just looks like something that exploded, like fireworks that went wrong. The green looks like the smoke from the fireworks, and the red looks like sparks that are still flying. You can almost picture that. Supernova exploding. Well, that's what this is. It's the remains of that supernova explosion. Pretty fun, right? So this is a unique object. It stays in the same place in the sky, just like all the stars do. But it is kind of expanding and changing over millions of years, but not fast enough for us to tell it. Okay, so that's the Crab Nebula. Do a quick log entry. Really does look like an exploding star, like fireworks and smoke. Okay, we've got, oh, we should go see the moon. First, let's save a picture of this. It's out of focus a little bit, so, oh, we might as well. And then let's stop live stacking. And let's set our time on like 0.2 seconds. And leave it at 100 for now. And then let's slew to the moon. The moon looks so bright if you don't prepare for it.
The telescope is slewing. Viewing moon.
Thanks for joining us, Junk John. You're very kind. Wow, that is so bright, isn't it? Let's go with 0.8. No, let's go with 80 milliseconds. Let's go with 30 milliseconds. Let's go with 5 milliseconds. Okay, now we're getting warm, aren't we? Let's go with 2 milliseconds. Okay, so the moon. Now all these different areas on the moon, they all have names. And our atlas here can help us identify those names. You notice it's mounted sideways again. Aw, Sky Tools encountered a face. Aw, OBS Studio closed. Okay, I think we might have experienced a blip. Are we back yet? Can you guys tell us, are we back? Okay, I think there was a blip in the internet or something. When I click this OK, it might close Sky Tools, so I'm going to get that out of the way for a minute. And let's see what we can see before it closes. Okay, so it's on its edge. This is the Mare Sinitatis, which would be called Serenity Sea of Serenity, that's what it'd be called. Mare Serenitatis. This part of the moon would be called Mare Tranquillitatis, Sea of Tranquility. And the Apollo 11 astronauts landed right around in here. So if we could zoom in tight enough, maybe we could see their flag and the lunar module. So let's see. Sea of Serenity, Sea of Tranquility, Mare Fecunditatis, Mare Nectaris, Mare Crisium. Wish we could turn this. Wasn't there a way that we discovered the other night, guys, to turn this? Remember? I think we put it on eyepiece and turned it, and didn't that turn this atlas? Oh well. Anyway, and then all these craters have names, like this crater. Or is that here? This must be called Copernicus. My goodness, it zooms in quickly. This is called Copernicus. This is called Tycho. You get the idea. All these things have names. Pretty fun, right? I think a lot of people get a big kick out of studying the different images on the moon. I've never been, a big moon crater fan, but I think it's interesting. It's going to be bright. Let's switch this back into night vision mode. This thing crashed. Sky Tools did. It happened when we brought up the moon. Must have just been too much data for it. That Opal guy. Good to have you back, that Opal guy. You need a really good zoom to see the lunar module and the flag. You're right. Let's do a quick log of the moon. We identified several seas and craters. Fascinating. All right, let's go to the Orion Nebula. Oh, connect to the telescope again.
Telescope connected. The telescope is slewing.
There went the moon. Kevin, good to have you aboard from LA.
Viewing Orion Nebula.
If you guys have tuned in late, what we've done tonight is try to gear some of the discussion, not all of it, but some of it, to a younger audience. And we've talked, for instance, to the son of one of my coworkers here. The coworker's name is Ross, and his wife Megan. They have a son Judah. So we've tried to talk directly to Judah sometimes. And Judah, I hope you're still with us. What we're going to see here is the Orion Nebula. Let's put this on maybe 15 seconds. And then let's change the name here to M42. And
Viewing Orion Nebula.
okay. Now, Judah, do you remember what a nebula is? Remember, it's a cloudy place. And remember what makes the clouds light up in space? Remember, it's when there's stars? Well, there are 4 really bright stars behind this cloud. And those stars are right in here. Astronomers have given them the name the trapezium, like trapeze, and that's lighting up all of these gases. And anywhere you see something that's pink, that's hydrogen gas lighting up. And if it's kind of greenish, it might be oxygen. If it's whitish, it could be dust. And then there are other trace gases out there too, but most of it is hydrogen too, like halfway being lit up by the light behind it, like we talked about a fog, you know, the light lighting up the fog. This is a very relatively close nebula to us. You can see this with your naked eye. If you go outside and look for the constellation Orion, let's do this view first. So if you look toward the southwest, you'll see 3 belt stars. That's a sure sign you found Orion. And then you'll see a bright star up on the right shoulder. That's Betelgeuse or Betelgeuse. And then a star down here on the left foot, that's Rigel. You can see the other foot and the other shoulder and see him with his bow and arrow. You can see all that. It's a beautiful constellation. Well, there's like a sword here on his belt. And near the tip of the sword is this amazing Orion Nebula. It's really bright. Like, it looks as bright as these other stars in a way. Not quite, but almost. So let's close this and open up the atlas, because you'll see this entire area is just made up of hydrogen gas. And there in the middle is that trapezium of stars that are backlighting this whole thing. And over time, these gases all start collecting together and they form other stars. So what you're seeing here is like a... Did you ever go to the hospital, Judah, and your mom might have shown you through the window somebody's baby that had been born? They call that the nursery, where all the babies are. This is a star nursery, a place where tons and tons of stars are being born. Just as we watch this, stars that are coming together and being born. And what makes it so beautiful are all these gases. So this is M42, and then this part of the nebula is called M43. To me, it sort of all adds together. And I kind of look at it and kind of think it looks like the head of a bird that's a big turkey or something that's opening up its mouth to eat a worm that its mother is going to place in its mouth. And it's spreading its wings and it's going... Bark, bark, bark. See that? M43 is the head. All of this, M42 is the body and the wings. Man, it's beautiful, isn't it? Wow. Can you believe what amazing stuff God can make? Distance-wise, we're really close to this. I forget the distance. Do you guys remember? Let's go see the distance real quick. Distance to the Orion Nebula. 1,500 light years. Look down in here, the way it must be like darker dust that's keeping us from seeing the light behind it. So it's like a dark nebula. This is like dark nebula. Now this is a different nebula over here, and this is sometimes called the Running Man. And for a long time I couldn't see why, and then the other night on this channel people helped me realize the man's upside down. These are his legs, and he's got his arms out, and that's his head, and he's running toward the Orion Nebula. So it's upside down. Pretty cool, huh? It's amazing. Always amazing. M43. $16,000 light years. Kevin says, my first education in astronomy came from Dinsmore Altair, who was director of the Griffith Observatory in LA. I was 10 at the time. Dr. Altair wrote or edited several books, including Lunar Atlas. Oh, that's awesome. Boy, this is just so beautiful. That's just 7 minutes of integration. That means we've been taking pictures here for 7 minutes, Judah. And look how beautiful that is. I mean, this entire area is filled with gases. All right, it's 25 after, so we've got time for one last object. Let's go back over here and look at our list and see. How about M3? Because isn't M3 a globular cluster?
The telescope is slewing.
We've looked at open clusters, but we haven't looked at globular clusters yet. It was, Dean. It was a very clear shot, wasn't it? Probably won't need but 3 seconds here.
Viewing M3.
Odd. Okay, here we go. So sometimes, remember we said open clusters are just a group of stars traveling together.
Viewing M3.
Sometimes the stars travel together in a little bit tighter format. Look at these. When stars look like this, we call it a globular cluster instead of an open cluster. So you might have maybe you've thought about, Judah, in the past, a glob of Play-Doh. A glob of Play-Doh. Well, this is a glob of stars. And look how the center is almost like a snowball. It's so tight. And here's what's interesting about the glob of stars, the globular clusters. They don't travel in the same circle as the open clusters. Like in a spiral galaxy, they buzz around the entire disk like they're bees, and they go outside the disk. It's kind of odd. And they also are a lot older. Globular clusters can be, and I talk about age as being apparent age. The apparent age of a globular cluster can be 3 billion years old or more. 4 billion years with a B, bravo. It's really, really old. They would be like the grandparents of all the stars. And the reason why I say that it's the apparent age is because God could have created the universe so that it already looked old when he created it, just because that's what God does. He didn't, when he created a tree, he didn't like first make a little acorn and then make it grow for 100 years. When he created a tree, he just created a growing tree, even though it was already growing. So that's what God does when he creates things. He can create things if he wants to. He can create them as if they've been living for a while. So the apparent age of this, whenever God created it, right now, it looks to us like it's 3 or 4 billion years old, which is amazing. It's so old. And this is traveling around galaxies instead of in it. So that's what you might remember. And there are a lot of stars there. And they're all different colors, but they tend to be like greenish and whitish. And these are globular clusters. So let's review all the different things we've seen. I'm going to make a quick little log entry of this. We've seen globular clusters like M3. We've seen asteroids like Juno. We've seen planetary nebulae like the clown face or the Eskimo Nebula, remember? We've seen other asteroids, Herculina, tiny. We looked at the surface of the moon and saw the craters and the seas. They don't really have water in them. They just look like they do. That's what the early astronomers thought. So they named them seas. When we got there, we found out they were actually just flat places where maybe volcano had spilled its volcanic lava across and made it really flat. We saw supernova, the remains of a supernova, the Crab Nebula M1. We saw open clusters like M45, the Pleiades. We saw the Hyades, which is a loose open cluster. We saw comets like 2017 K2 Pan-STARRS. We saw big spiral galaxies like Andromeda and Triangulum. And then we saw planets like Uranus and Jupiter with all their moons spinning around it. We saw the suns of Vulcan. So if you pretend like Star Trek really happened and Mr. Spock was on his planet Vulcan, he'd be looking up at those stars like Keyed, that we saw. Remember they're double and triple sometimes, so he would see 2 and 3 stars that were above his planet, making it very bright, maybe even so bright that at night it didn't get all the way dark. Who knows? In all of this, we've marveled at the way God made the universe. And you were here for the whole time, I hope, Judah. And you guys were here too. Tiffany, thank you for hosting everybody. Like you say, you just said a lovely evening with wonderful people. Thanks, that Opal guy, for being here. Corin and Dean and everybody else, Stu, that stopped by. We appreciate the times that you stop by. If you like content like this, we'd encourage you to subscribe. That helps get the channel up in other people's heads-up radars. You could hit the bell and hit like, and that makes sure that you see it when we're live streaming like this. You could go to emeraldhillskies.com and fill out the little subscription form. It's just a quick little form, and then you'll get an email notice when we're going to do a live stream like this. We try to do one per week during whatever night we can find that's clear. And thanks for being a part of this. We continue to learn, and we hope you do as well. We'll look forward to seeing you next time. God bless and good night to everybody. Dean says, thanks for the sky tour. I enjoyed hanging out with everybody. Night, night. And the same to you, Tiffany, and everybody else. Good night and God bless. And we'll say good evening from Emerald Hills. Good night.